Alright, so here we are for the last video for Unit 5.1, this rotational motion and gravity. So we're going to look at Kepler's laws and look at satellite motion. Alright, so just a way to think about this, what are some examples of objects that are in gravitational orbits? Okay, I mean you've got these artificial man-made satellites that orbit the Earth, right? Communication satellites, Sputnik, things like that. There's astronomical debris, right, that is orbiting around out there. You have comets, meteors, right, things like that are orbiting. The planets are in gravitational orbit, right? So you could just think of there's just a lot of examples of objects in gravitational orbit. But one thing to note is that all these objects have two things that are, essentially the same characteristics, right? So you're going to have a small mass, right, orbiting a larger mass, right? So that's the first thing, right? So if I have Earth in orbit, and even the moon, right, or a satellite, right? So I have an Earth that's got a mass of big M, and I have a satellite with a mass of little m, right? So I got a small mass orbiting this larger body. And guess what? This is one of the reasons why Pluto is no longer a planet, okay? Because Pluto's moon is very close to the size of Pluto. Okay, that is one of the reasons that Pluto is no longer a planet, right? So you guys may have grown up in a school system that only had 8 planets. I grew up in a school system that had 9 planets. So my generation had to adjust to your generation in the idea that Pluto is no longer a planet. Okay. The second one is that the system is isolated from other masses. Right? Remember, we talk about isolated systems, right, where mass or energy is not allowed to flow in or out. Okay, and so the way we think about it is that when the moon is in orbit around the Earth, that when we say Earth-Moon system, there's nothing else that we're encountering. Right? If we're talking about an artificial, let's say Sputnik and the Earth, there's nothing else that we're encountering. Right? As long as everything is good in orbit. All right. So these conditions are satisfied to good approximation by Earth's satellites, including the moon, by objects orbiting the sun and satellites or other planets, right? So all this stuff is all kind of, intertwined, these two conditions, right? So the main focus of this particular section is not necessarily to look at satellite motion, although we will calculate the speed of satellites in orbit, okay, and look at, how high do geosynchronous orbit, what is geosynchronous orbit, how high do the objects have to be placed, okay? But we're also going to look at Johann Kepler, okay? So Johann Kepler was a German astronomer who did work with a Danish astronomer, and there's a lot of argument, how do you say this guy's name, but it's Tycho Brahe, okay? So he was a Danish astronomer who collected a lot of data, and Kepler was actually his assistant. And now there's a lot of controversy about how does Kepler get this data. Did he steal it from Brahe's family? Did Brahe actually will it? Did Kepler inherit it from Brahe? It's just kind of like this ongoing argument between the families. Okay, how does he get this data? But the data was very meticulously recorded, especially this is the time way before telescopes were even invented. And this guy plotted the planets, where these planets are sitting. Okay, now he didn't do much in terms of the actual data analysis. That was all left up to Kepler. And what Kepler discovered, that there were 3 laws of all the planets, okay, that govern these planets. Okay, the first thing is what is called the law of ellipses. Okay. If you take, or when you take, or if you're currently taking pre-calc, you will study conic sections, okay, and you'll learn that one of these conic sections is called an ellipse. So the law of ellipses says that the orbit of each planet about the sun is an ellipse with the sun at one focus, right? And so here's my ellipse. In fact, they're not. So they're nearly they're technically elliptical orbit, but we say that they're actually a near concentric circular orbit, right? And what a concentric circle is just a circular orbit. Okay, and if you actually look up at data, I think I didn't put it in this one, but in one of the other notes documents, I actually put a table of all the ellipses. The eccentricities, which basically tells you, excuse me, how elliptical the orbit is. You're going to find that the eccentricity of the planets, like it's 0.0 something, where a circle has an eccentricity of 0. Okay. So that's the law of ellipses. The second one is what we call the law of periods. The law of areas. Law of periods is the third law. So the law of areas, and that's what this little diagram over here says, okay, says that imagine if I had a line, right, connecting the planet to the sun, and as the planet goes from position A to position B, it sweeps out this area. Okay, and then we do the same thing. We kind of connect it at position C, and then we let it sweep out to position D. And then we go all the way out here, right, to E and F. The law of area says that area 1 equals area 2 equals area 3. And officially it says that each planet moves so that an imaginary line drawn from the sun to the planet sweeps out areas in equal times. So let's say this is a 10-day period, right? This is a 10-day period. This is a 10-day period. And so as long as the time frames are the same, right, they're going to sweep out equal areas. Sorry, I was trying to write it. Okay, so it sweeps out as long as they're equal time frames, all those areas would be the same. Okay, and this is very characteristic. Whenever the planet is further away from the sun, it moves a lot slower than when it's closer to the sun. Okay, and then finally the last one is called the law of periods, and this is the one that actually brings in a mathematical relationship, okay, which says that the square of the periods is equal to the ratio of the square of the periods is equal to the ratio of the cubes of the radii. Okay, and you can get it even further by saying that this ratio of T1 squared to R1 cubed is equal to a constant. Okay, and I can look up what that constant is real quick. It's usually published somewhere. The main thing is this right here, right, is this mathematical relationship. Okay, and we're going to look at a couple examples with that, using that mathematical relationship. Okay, so this question says, given that the moon orbits Earth each 27.3 days and that has an average distance of 3.84, this should say times 10 to the 8th, not to the 4th, meters from the center of the Earth, calculate the period of an artificial satellite orbiting at an average altitude of 1,500 kilometers above Earth's surface. Okay, so what we're going to do is we're going to take the moon's info, right, and it tells us that it has a period of 27.3 days with a radius of, and we'll call this moon, so RM and TM, of 3.84 times 10 to the 8th meters, right? And we're looking at a satellite, right, which we don't know the period, and they tell us that the, now this is where it gets a little complicated, especially with this, when we talk about planets in orbit. So the measurements are from the center of the Earth. And so what that looks like is, if I have my Earth here, right, I have the radius of the Earth or the planet, and then if my satellite is sitting out here, a height off of it, I end up with this equation down here. And so that's the radius that we're looking for. So remember, gravity generates from the center of the Earth, And that's where this comes from. And so what we have to do is we have to take the radius of Earth and add it to that height. So the radius of Earth is 6,300 kilometers, and it tells us that we're 1,500 kilometers up. So we're at 7,880 kilometers, or 7.880 times 10 to the 5th meters, okay? Or it could be to the 6th. 780 times 1,000. 1, 2, 3, 4, 5. It is 6, sorry. So this should be a 6. Okay? And so all we're going to do now is say, okay, T moon squared over T. In fact, to make your algebra easier, put your unknown in the top already. That's just a little free trick of the day. Right? And so we're going to say T satellite squared over T moon squared is equal to R satellite cubed over R moon cubed. So remember, it's unknown to unknown, right? Known to known, the way this kind of works out. And so what do I do? That all that means is I just have to multiply Tm squared up, right? My known moon, and then finally take the square root of both sides. And so Ts would be the period of the moon times the cube of these radii, okay? And so the period of the moon, 27.3 days. And I can leave that. I don't have to convert that, because I can just say, okay, I'm going to talk about my period in days, right? I may want to talk about in hours if I find that it's a lot smaller, right? A lot smaller value. And I'm going to take the square root of my distances. So I'm going to do the satellite. So 7.8 times 10 to the 6th cubed, right? Divided by 3.84 times 10 to the 8th cubed. Okay. You can also do a little bit of algebra here by just simply like cubing that ratio. And so I'm going to do square root, so 27.3 times the square root of 7.880 cubed divided by 3.84 E8 cubed, okay? And I get a period of the satellite of 0.08, sorry, I can't write right now, okay? So it's going to be 0.0803 days, right? If I multiply that by 24, I get 1.93 hours, right? So the satellite would take roughly 2 hours to go around the Earth, okay, at that location, all right? Now, one thing that you can do with these equations, again, we can equate some of this stuff back to Newton's laws and use some of our other formulas. And so to determine the speed of the satellite, you're just going to simply do the square root of g, the mass of the planet, divided by, and I'm going to call this r sub o, right, which is the orbital radius. I'm going to grab a pen, not the squared. Okay, but remember, RO is RP plus H, right? And so if you want to, you can even further put that in there. So it's like GMP, mass of the planet, over RP plus H squared. Okay, so either one. And what that does is by saying, okay, my centripetal force equals my gravitational force, so mv squared over r would be gm, mass of the planet, over our orbital radius squared. Do a little bit of algebra, and you end up with that v equals the square root of gmp, r orbital radius squared. Okay, so here is our final example problem for this unit. Okay, so a geosynchronous satellite is a satellite that orbits the Earth with an orbital period of 24 hours, thus matching the period of the Earth's rotational motion. A special class of geosynchronous satellites is a geostationary satellite. So a geostationary satellite orbits the Earth in 24 hours along an orbital path that is parallel to an imaginary plane drawn through the Earth's equator. Okay, such a satellite appears permanently fixed above the same location on the Earth. If a geostationary satellite wishes to orbit the Earth in 24 hours, which is 86,400 seconds, then how high above the Earth's surface must it be located? Okay, and so you got the mass of the Earth, 5.98 times 10 to the 24th kilograms, and you have the radius of the Earth of 6.37 times 10 to the 6th meters. Okay, so what does that mean for us? What we're going to need to do is do a fair amount of algebra here. Okay, that's kind of some of this of what happens, right? And so the first thing we're going to do, okay, is that we're going to say that the speed of the planet, okay, or the satellite, right, is going to be just like we did before, right? We did one question, I think, in the previous video where we did 2 pi over t. So the speed of the satellite is going to be 2 pi the circumference that it's going to travel over the time. Okay? But we know that's going to equal, and this is going to be our orbital radius, but we also have that AC, the centripetal acceleration, right? Or in fact, we can sit there and say v squared over r equals g mass of the planet over r squared, right? And this is all orbital, okay? And so what I can do is clean this up a little bit right now. So this is going to cancel that. And so this is where I get my v squared equals, in fact, I messed this up here. This should not be squared in the denominator. It should be just simply to the first, right? So I'm going to get g mass of the planet over our orbital radius, okay? And what I'm going to do is kind of work this backwards, right? And so this isn't v squared, this is v, right? And so, in fact, I can really start my algebra here. I keep putting the erase things, right? And so I can say that v squared equals g mass of the planet over RO, okay? But I can also do some, plugging in this 2 pi RO over T. I can plug that in as well. But if I solve this for RO, and all I'm really going to do is G mass of the planet over T, or sorry, not T, but V squared. So it's going to be V squared, right? And if I want, if I square V, this 2 pi RO over T, right? If I square all this, I end up with 4 pi squared RO squared over T squared. And I take that and plug it in there and do a little bit more algebra, right? So this algebra does look like it's going to kind of get messy. So I'm going to say RO equals GMP. Now when I plug that in, my T is going to go up to the numerator, and then I'm going to end up with this 4 pi RO squared. Okay, and so something you see here, there's my RO again. I need to bring that up, and so this is where I really get that RO cubed. So it's going to be RO equals GMP T squared over 4 pi squared. Okay, and now I can just simply say RO. I know I'm all over the place. I apologize for that. So RO is going to be the cube root of GMP T squared over 4 pi squared. And so now I can plug in numbers. So I'm going to take the cube root of 6.67 times 10 to the negative 11th times the mass of the planet, which is the Earth, so 5.98 times 10 to the 24th, times the period, so we want to do this in 1 hour period, or 1 day period, so it's the 86,400, divided by 4 pi squared. Now, this is going to give me the orbital radius. It's not going to give me it's not going to give me my answer, right? Which means then I have to subtract out the radius of the Earth, right? So I'm going to do 6.67 e negative 11 times 5.98 e 24 times 86400 squared divided by 4 second shift pi squared. and I get an orbital radius of 1, 2, 3, 4, 5, 6, 7. 4.23 times 10 to the 7th meters. And so I go back to my RO, right? I do have a little bit of sliver of stuff down here. So, right, so now I'm going to do RO equals RP plus H, which makes H equal to RO minus RP. And so it's going to be 4.23 times 10 to the 7th minus the radius of Earth, which is 6.37 times 10 to the 6th. Sorry, I ran into the page number there. So 4.23 exponent 7 minus 6.37 exponent 6. And I get a height of 3.59 times 10 to the 7th meters. Okay, so just to give you a comparison, the International Space Station, okay, let me look that up. The International Space Station is 254 miles. Let's put that in meters. It is 408,000 meters, right, above the Earth. So you can see that it's not in a geosynchronous orbit because we're way smaller, right, than that. Okay. So I know this problem was everywhere, right? So the main thing is here, and then working your way to get down to RO, right? So if you see this, this GMP over T, or sorry, not T squared, but 4 pi squared, this is what that ratio equals that I mentioned before. And it will change, around the planets, 4 pi squared. So this is going to be our ratio of r cubed to t squared, right? And so if you go back up here where I talked about it's equal to a constant, okay? So in fact, what I have written up there is the inverse of what you see right here, okay? And so you can kind of figure out what is this planetary motion constant, if you want, that's what you want to call it, for Earth, for the Moon, for Jupiter, for Mars, right? For all these different planets. So that ends Unit 5.1, rotational motion and gravity. We will start the videos for 5.2 shortly, but that's going to focus around rotational dynamics as well as torque and statics and all that stuff. Okay.